Hello, everybody. I'm going to work a classic problem which involves using a heavy pulley. In this case, it's a pulley that the tension is spent to rotate the pulley. So it's going to be a little bit different than what we had done before. Okay, so the first thing we want to do is parse the problem. So there's a steel ring So the mass of the ring is 30 kilograms, has a radius of 2.5 meters. Okay, it is connected to a motor at the middle, which means we probably have spokes, lightweight spokes connecting it in. Okay. So we've actually just been given the question in this problem. You need to determine the total torque it can apply. So the question is, find torque applied by motor. Okay. I probably should have made that a little bit more distance on me, so let me see if I can't erase question. And just make it a lot shorter. Okay. But what we're having then is two different tensions. On one side, a cable goes down and connects to a to the elevator car itself, and the mass of the elevator car was 400 kilograms, and that's all we know. It runs over the steel ring and connects to a stack of counterweights. If you've been in some places with elevator mechanisms that kind of show, you can see the big counterweights. It may even be in Captain America Avengers Winter Soldier, where you see the counterweights in action. Anyways, we have the mass of these weights then are set to be 300 kilograms. And the elevator slowly moves up with an acceleration. And that acceleration of the elevator car is given to be 0.5 meters per second. That should be squared in there. When first moving up. So that's all the information from the problem. Let's talk about our approach. We are looking for the torque applied by a motor, so let's find the torque for this scenario. And in this scenario, we can use this version the torque around the same axis is equal to the moment of inertia and the angular acceleration, because the center of mass of the pulley is at rest. So this is our big assumption. Keep in mind, if it wasn't at rest, the whole thing would be falling down, which is the stuff of a disaster movie, not the stuff of an elevator problem. Given that, let's do our first approach. So our first approach is going to be torque. And what we wanted to do was, go away. What we wanted to do was sum all of the torques about a common axis. And let that equal then the moment of inertia about that common axis and the angular acceleration. All right. So we need to sum the torques, and we're going to get the, we're going to need the forces. And the cross products. So that we can sum torques. So we're going to have a force tension down to the elevator car. I think we're using C for car. I'm going to have a force tension down to the counterweights. The wheel is going to give us the force of the gravity on it and the force of the motor shaft, which applies all of this upward. Okay, so the force of the car, we don't know. We do know it's located at a distance r, force torque of the car, and the cross products, if we assign our usual x and y, the force on the car is going to be, to get to the car, I have to go this way with r. And notice that is a negative x hat direction. And the force from the elevator car, when the system is our wheel, is also pointing down. So that's going to be minus y hat. We pull our circle into place, so we have it. And we can produce the final answer by knowing x and y, well, x is negative and y is negative, and two negatives make a positive. And then we start at x, we grab y, we end up at z. So this is going to be r force of the tension on the car in the z hat direction, positive. the force of the tension of the counterweights, come on, tension of the counterweights, R comes out this way in the positive x direction. So we get R, force of the counterweights, tension, and then we get R is a positive. Why do I keep getting that pen? R is a positive x hat crossed into a negative y hat. So the negative is going to carry out in front. And we're still doing x cross y to find z, only now it's negative R force tension of the counterweight in the z hat direction. I'm just going to make a note that our system here is the pulley, just for when you go back and review this material. Back to our blue pen, and the force of gravity acts at the center of mass. So I'm going to get R center of mass crossed into mg. And we know that that distance is 0 between the center of mass of the wheel and the center of gravity of the wheel. They're the same thing. So we go to 0. In the force of the shaft, I don't want to get into the details, but we do know there's going to be a torque from the motor in this problem. And the torque supplied by that motor had better be in a z hat direction. So we can sum all the torques, and we'll see that R force of the torque of the car minus R force of the tension from the counterweights plus the the torque of the motor. This all equals I alpha. So in this blank space we have left, when we're talking about the system of the pulley, we know for a ring I equals mr squared. And if the cable is turning without slipping, so the no slip condition, that tells us that the velocity at the the velocity of the cable is just equal to R times how the cable, the rotation, the angular rotation of the wheel. And the first derivative reminds us that alpha is equal to R alpha. Let's get that fixed. And velocity turns into a linear acceleration. This allows us to take the I alpha, turn it into m of the What do we use? Radius. Mass of the ring, radius squared, and then the alpha becomes A over capital R. Sufficiency, always a good question. So let's check. Do we know the force tension on the car? We don't, because there's an acceleration on the car, which means there's an acceleration associated with the counterweight. This is what we're hoping to find. And we know I, and we know the radius, and we know the mass of the ring, and we know the acceleration. So we do not have sufficiency. No. We need to find these two forces. To find a force, the best place to start is with Newton's second law of motion. So the system on this case is going to be the car, and we're going to go about using sum of the forces equals mass and acceleration. As soon as we've made this decision, we can recognize that all of this is happening in the y direction, so we don't have to worry about x. We draw a free body diagram with the force of the tension in the car counteracted by the force of gravity of the car, with a reminder that we have an acceleration, and we can probably then put our y-axis in that same direction. So we sum the forces, we get the force. Let me switch to the blue pen at this point. So I'm going to get, when I sum forces in the y direction, I'm going to get a positive force tension on the car. I'm going to get a negative force of gravity of the car, and that has to equal the mass of the car times the acceleration of the car. So we came in here, we were looking for FTC, and what we'll find is the mass of the car, the acceleration of the car, plus the force of gravity acting on providing the tension for the car system. We'll go back to black so we can do our next approach. Our next approach is to find, with the system of the counterweights, we draw we can sum the forces again in the y direction, mass and acceleration in the y direction. We can draw a free body diagram, force tension of the weight up, the force of gravity of the weight down, As one side of this system goes up, the other side has to go down, and we're going down without slipping. So let's align our y direction with the downward direction. Let's return to summing the forces. And so let's return to our blue pen. And we're going to sum our forces, technically in the y direction. Now I get the force of gravity of the weight in the positive direction minus the force of tension in the weight. And that's going to equal the mass of the weights and their acceleration. We came in here to find the force on the weights. So that's going to allow us to do some swapping. I'll bring that to this side and bring this term to that side. So I can then write the force, the tension of the weights is equal to force of gravity and the weights. That minus becomes positive. This is going to come over and become negative. Mass of the weights and the acceleration of the weights. Or more simply put, mass of the weights, gravity, mass of the weights, and the acceleration of the weights. Before we leave this and move on to our solution, we want to point out that the no-slip condition here tells us that alpha is the same throughout all systems, which means the linear acceleration is the same for all systems. All right, so we did our two approaches. Now we're ready to do our evaluation step. Where we transport the equations into one place to make our lives easier. So we have our FTC minus our TW plus the torque of the motor and that all equals the mass of the ring times R and acceleration. The force, the tension on the car is going to equal, I'm going to pull the masses out so that we wind up with mass of the car and then G plus A, and the force of the tension from the counterweights is equal to the mass of the counterweight, G minus A. So let's go ahead and put in our values and solve for the T of the motor. So the torque on the motor is just equal to the mass of the ring, the radius of the ring, and the acceleration, which we know, minus r ftc, so r mass of the car, g plus r acceleration, then plus capital R, the force from the weight, which we'll do the same simplification for and get R mass of the weight, g minus the acceleration. If we think about this in terms of units before plugging in numbers, we do kilograms. I just always do that. I guess I like red crayons. We always wind up with kilograms, meters, and our acceleration, meters per second squared. And that's true in each and every case. We've got our we've got our meters, we've got a kilogram, we have our acceleration. And acceleration over here, the kilograms, and the distance. So at this stage of the game, everything is adding up to the units of torque, which is okay. Yeah, right. Which is adding up to the torque. It's just R cross F. So the torque is distance, and forces are in newtons. And with a newton being a kilogram meters per second, or a newton being a kilogram times acceleration, our units at this point are working out fabulously. I'm going to pull the radius of the ring out. So the radius of the ring was 2.5 meters. So I'm going to be able to go 2.5. Oops. Yeah. And the mass of the ring was 30 kilograms times our small acceleration, 0.5 meter per second squared. Minus the mass of the car, which was 400 kilograms. And here we're going to do 9.8 plus 0.5, so 8 and 5 is 13. So this is going to be 10.3. And we add in the mass of the counterweight, which was at 300 kilograms. And we're going to multiply it by the acceleration g subtracted by the small amount. So that's going to give us, let's see, 9.8 minus 5 gets us down to 9.3. Okay. Let's see how we do in all of this. Unclear. I'll put the 2.5 in last. I'm going to have 30 times 0.5 minus 400 times 10.3 plus 300 times 9.3. And we multiply that by 2.5, and we get the answer of negative 3.29 times 10 to the 3 meters newtons. Do a quick review of our work. Negative? What's going on there? Well, let's get our highlighter out. When we did our torque equation, we assumed that we had plus T on the motor. We didn't know the direction of Z at all, Z hat at all. We just hoped that this torque would be positive. In reality, the torque is negative, so all that means is we assumed the initially wrong direction that the motor has to spin. So this is nothing to worry about. I keep hitting the crayon, that's just funny. The torque of the motor is negative Z hat, which if we go up to the system, sorry if you got seasick there, if we have to lift the car, if we have to lift the car to go around this way, that means the torque of the motor is in the negative Z hat direction. Because remember, clockwise is negative, counterclockwise is positive. So I'll do a quick record of that down here. Plus Z hat is from counterclockwise movement. And negative Z hat just comes when we're moving clockwise. So it's one of the rules we have to keep in the back of our head. So again, it makes sense that the motor should be running, the torque of the motor should be running negative. The value? So we've got 3.3 kilonewtons. Kilonewtons times the mass. I'm sorry, times distance meter for the torque. I'm actually surprised it's this low. It may have to do with the fact that our acceleration is very small, and that we're just crawling up the elevator shaft. So it seems small, given the 400 kilogram and the 300 kilogram masses. But it's reasonable. And we've already talked about, let's keep it in crayons. It's about where my brain is anyways. The units we did we can check them off because cran movement up to here, we've already demonstrated our units work. I hope you find this example problem useful, and I'll be talking to you soon.